Welcome to today's Explainer. So we're going on a bit of a journey today, and our starting point is, well, it's probably sitting in your pantry right now. We're going to use the everyday, universally frustrating annoyance of a stale potato chip as a sort of Trojan horse. Yeah, you heard me right. Through the lens of that one, single, deeply disappointing snack, we're actually going to build an entire mind map of foundational chemistry. Get ready, because we are unpacking the invisible rules that govern why your food degrades, and how that perfectly connects to the fundamental laws of the universe. Let's dive in.
I mean, we've all been there, right? Picture this. You reach into a bag of chips or maybe a box of biscuits that you folded over and left in the pantry a few days ago. You've got this false sense of security. You take a bite, totally expecting that satisfying salty crunch, and instead, you get that terrible, limp, cardboard taste and that faintly unpleasant, stale smell. It is just a complete betrayal of the snack experience. So today, we're going to treat that folded chip bag exactly like a chemical crime scene. We need to answer a crucial question. Why do good chips go bad? Like what invisible, relentless forces are at work inside your snack cupboard while you sleep?
Well, the main culprit behind this pantry crime is a process called rancidity. It happens when the fats and oils present in your food get oxidized. Now, this isn't just food, getting old. It's actually a very specific, microscopic theft. Oxidation happens when oxygen molecules interact with fats and essentially steal their electrons. They literally break down those stable molecular bonds and create entirely new, totally foul-smelling compounds. So when you get hit with that stale flavor in an old chip, you aren't just tasting age. You are literally tasting a chemical reaction. You're tasting oxidation in real time.
But, hey, the good news is we aren't entirely defenseless against this microscopic siege. Food manufacturers and, honestly, savvy consumers like us have developed specific, highly effective countermeasures to fight back against this relentless oxygen attack. Because oxygen is constantly bombarding our food, constantly trying to break down those fat molecules, we have to build a fortress. If oxygen is the enemy trying to ruin our snacks, well, we need a targeted defense strategy to stop those chemical reactions in their tracks and, ultimately, protect the crunch.
So, how exactly do we fight back? We've got 4 main methods of prevention. First up, adding antioxidants directly to the food. Think of antioxidants as, like, sacrificial molecules. They proactively offer up their own electrons to the oxygen so the fats in your chips don't have to. Pretty neat, right? Second, storing food in airtight containers. That creates a literal, physical barrier against the surrounding air. Third is refrigeration. Now, why does cold help? It's all about kinetic energy. Cooling the food slows down the movement of the molecules, which drastically reduces the rate that these oxidative chemical reactions can even happen. And finally, packaging snacks in nitrogen gas. You know that giant puff of air inside a brand new bag of chips? It's not just empty space designed to trick you. It's actually a brilliant, deliberate tactic. By flushing the bag with nitrogen gas, which is highly unreactive, by the way, manufacturers displace the oxygen entirely. They are effectively hitting pause on rancidity before you even pop the bag open.
Now, this microscopic battle in your chip bag is just one tiny theater in a massive chemical universe. Let's zoom out for a second. The rancidity ruining your snack is a prime example of chemistry at work. But how do we actually know when a chemical change is happening? Well, there are exactly 5 distinct telltale signs. When substances interact, they might produce a noticeable temperature change, getting unexpectedly hot or cold. They might emit a gas, bubbling and fizzing. You might see a sudden color change, kind of like a slice of apple turning brown on the counter. They could emit light or fire, like a sparkler burning, or they might form a precipitate, which is just a fancy way of saying a solid suddenly appears when you mix 2 liquids together. Whenever you spot one of these 5 signs, you know the chemical universe is shifting.
And here's a fundamental truth about all of this. In chemistry, absolutely nothing is lost and nothing is created out of thin air. Scientists don't just passively watch these reactions happen. They write them out as perfectly balanced equations. This is the law of conservation of mass in action. Whether a reaction is happening inside a crumpled chip bag or a high-tech laboratory, the number of atoms you start with must equal the number of atoms you end up with. No exceptions. Plus, these equations come complete with state symbols. Those tell us if a substance is a solid, a liquid, a gas, or dissolved in water. It's a system that ensures every single atom is strictly accounted for, bringing perfect mathematical order to the crazy chemical changes happening all around us.
Now, despite the billions of chemical changes happening across the universe every single second, they can actually be fundamentally categorized. It might seem like total chaos out there, but it all boils down beautifully to just 4 main types of chemical reactions. And understanding these 4 distinct categories, that gives us the master key. It lets us decode exactly how different elements and compounds interact with one another to build the world around us, and yeah, occasionally ruin our snacks.
First up, let's look at combination versus decomposition. These are essentially the first 2 fundamental laws of our chemical universe, the ultimate yin and yang. In a combination reaction, simpler elements are coming together to form something entirely new and much more complex. Think of hydrogen and oxygen gases combining to form liquid water. Boom, combination. Now, in a decomposition reaction, the exact opposite is happening. A complex substance is breaking down into simpler parts. An everyday example would be hydrogen peroxide degrading into water and oxygen gas over time. It's just this beautiful, continuous cycle of building things up and tearing them down.
To round out our set of 4, we have displacement versus double displacement. These are really all about the swapping of elements. Honestly, think of displacement like a middle school dance floor. In a simple displacement, one highly reactive element taps another on the shoulder, cuts in, and totally steals its partner in a compound. But in a double displacement, oh, that is a full-on mutual swap. That's where 2 compounds trade partners completely to form 2 entirely new chemical pairs. So, together with combination and decomposition, these 4 types form the structural pillars of literally everything happening in chemistry.
But, it's not just about the physical shifting of atoms and dancing elements. We also have to talk about the invisible energy that powers these changes. Energy-wise, chemical reactions are categorized into 2 distinct camps: exothermic or endothermic. Exothermic reactions actively release energy into their surroundings. They literally feel hot to the touch, like the heat radiating from a roaring campfire or, cracking a hand warmer in the winter. Endothermic reactions, on the other hand, act like a sponge. They require the absorption of energy from their surroundings to even take place, which actually makes them feel physically cold to the touch. Energy is the ultimate currency driving every single reaction we've talked about today.
And that brings our entire journey full circle, because the overarching concept governing so much of what we've unpacked today is oxidation-reduction, or redox for short. This one concept is the root cause of so much chemical degradation in our everyday lives. It is the exact same fundamental science that is slowly rusting away a massive, heavy steel bridge through corrosion and, returning to where we started, destroying the crunch of your favorite potato snack through rancidity. It's all about the transfer of electrons, and it is completely universal. Whether it's taking down a skyscraper or a potato chip, the laws of chemistry remain undefeated.
So, having decoded the 5 signs of a chemical change, the 4 main types of reactions, the energy dynamics of hot and cold, and that constant, relentless threat of oxidation, I think we're left looking at our pantries in a completely new light. You officially have the mind map of a chemist. Which leaves me with a question for you as we wrap up this explainer. Knowing how relentlessly oxygen and energy are working around the clock, what chemical reactions are actively trying to destroy your next snack right now? Keep your eyes peeled, keep your snacks sealed, and as always, stay curious.